Here Mr. G, and we are going back to lesson 4. Now in lesson 4 we're going to be doing some revision. We're going to practice 3 questions related to the topics we did just previously, okay? So this is going to be momentum. We're going to be doing change in momentum as well as Newton's second law in terms of momentum. But in one of the questions there is also going to be some recalling from previous grades in terms of Newton's law of motion and a free body diagram, okay? So without taking longer, let's begin with the first question. This question, activity 1, have 2 sub-questions and it's going to be a multiple choice. You will always have multiple choice in your exams, okay? So multiple choice are those questions where you have to select the most correct answer. Now, not always they are very easy. Sometimes you do have to do some workout and do some calculation like these 2 I select for this lesson. Okay, so 1.1 says the ball with mass m, and we're going to be marking the data here. The ball with mass m, this is the mass of the object, of the ball in this case, strike a wall perpendicular with a speed v. Now, speed v, that is the initial speed. Okay, it's moving towards the wall. If it rebounds in the opposite direction with the same speed v, final speed is also v, the magnitude of the change in momentum, and then asking you to calculate the change in momentum, but the magnitude. Now, when they say magnitude, they asking you only about the number, the value, not the direction, but you must do the calculation, okay? So in this case, what we have is that you have a ball. Okay, so what we have is a ball that is moving towards a wall. It doesn't matter where the wall is, if it's on the right or on the left, it doesn't really matter. This is the initial, let's say, velocity of the ball, and the magnitude of that velocity is v. Okay, and then it bounces on the wall backward with the same velocity v. Okay, so now we have to select, before we answer this question, the direction you want as positive. So let's say towards is going to be positive. Remember, this is very important, and I ask you to please write it down. Write it down, don't just think it, but write it, okay? So toward is positive, and then we have this one. Therefore, this one will be minus v, because it's after. So now we're looking for change in momentum, okay? Now, change in momentum, remember, change in momentum is equal to mass multiplied by final velocity minus mass multiplied by initial velocity, okay? This is working with the same object. This is the ball. The mass of the ball did not change. So now here you're going to have a common factor. This is just to make it easy. You don't have to do it if you don't want. Mass bracket final velocity minus initial velocity. Now we're working with vectors. Remember, they only want the magnitude, but we first have to work with the vectors. So change in momentum is going to be equal to mass. Now we substitute the actual values, which is letters. Final v, but final v is negative. Okay? Final v is negative. Look here. Final v is negative. So it's minus v minus initial, which is v. When you solve this one, you have the change in momentum is equal to mass multiplied by minus 2v. Simple math. And if you fix this one, you will get that the change in momentum is equal to minus 2 mv. The minus here only means direction. So the actual final answer they want is the magnitude, which is change in momentum, equal to 2, let's fix that one, is it 2 mv. So, my lovely people, the correct answer will be A. So that is how you solve this first multiple choice. Please, you do have to solve it. You cannot guess. Multiple choice are never guess questions, okay? It's questions most of the time to be solved. So that was the first one. Remember, I posted in the community. I posted the questions, and I'll try to post the questions in the in the description of the video, so you can try to do the question before. Now, second question is very much similar with just few changes, okay? So this is question 1.2. And question 1.2 said a car of mass m, going back to the same type of data where you don't have actual values, you have just letters, move along a straight line with a velocity of magnitude v. So this is the initial speed of that car. The driver sees an obstruction and immediately applies the brake. The car stops uniformly in t seconds. So stops means that the final velocity, I'm going to write it here, the final velocity is going to be equal to 0. That means that stopped uniformly in t seconds. This is the time that they give you, t seconds, from the moment that the brakes are applied. The car does not hit the obstruction. Which one of the following represents the magnitude of the average force? Now, which one of the following represents the magnitude of the average force? Let's write the data here down of what we have. Now we have the mass of the car on this side. I'm going to write it. Mass of the car is going to be m. Okay. Now we have that the initial velocity, and I'm not going to write direction as yet. I'm going to write initial velocity is going to be v, and final velocity is going to be equal to 0. What else we have? The time, the interval time for that car to stop was t seconds. We don't have the actual number, we don't need it right now, okay? And then looking for the average net force or force, so I'm going to write F here, and I'm going to write F net is the only force acting there, or is the net force is what they want, so that's all they want, okay? So now this guy is moving in only one direction, it's only one direction, it stops, but it's moving in the same direction, so the forward direction is going to be positive, and therefore everything is positive. I'm going to write it forward is going to be positive, but it's not a need in this question because everything is moving in the same direction. Okay, so if we go to Newton's second law in terms of momentum, we have that F net is equal to change in momentum divided by change in time. And change in momentum, we just answer a question related to that one. So let's substitute here mass final velocity minus mass multiplied by initial velocity divided by time. And let's keep the vector symbols, even though it is not compulsory, right? But let's keep it. It's not compulsory here in South Africa, but maybe in other places it is. Okay, so here same story. We have working with the same car that did not change the mass, so we can say that the mass, the net force is equal to mass bracket final velocity minus initial velocity divided by time. And perhaps we can take this one just to not have it 2 and move it a little bit down. There we go. Okay, so I'm going to move up here. I don't have much space there, and then we can substitute now, guys. We can substitute what we have. F net, which is the average force they're asking you to calculate here, is equal to the product of mass. Mass is m according to the data, multiplied by final speed is 0 minus initial is v divided by t. Okay, now 0 minus v, this is a v, let's make sure you can see the difference there. So this one is going to be equal to mass multiplied by minus v divided by time. So if you solve this one here, you will have that is minus mv divided by time. But the minus, same as before, means direction. Means that the net force was in the opposite direction. Therefore, the magnitude of the net force will be equal to mv over t. That is the final answer, and therefore the answer is C. So I hope you understand this other question. Let's go to the next question. Okay, the second question said a car of 220 kilograms. Let's write down the data. The mass is 220 kilograms at rest. Now, at rest means that the velocity at that point is a 0. So the initial velocity is going to be equal to 0. On a rough horizontal road, here now the rough horizontal surface means that there is frictional force. That means that rough surface or horizontal road, the road is rough. From rest, accelerate from rest, as we said, the initial velocity is 0 to 100 kilometers per hour. And this one here is going to be the final velocity of this car. Now, we are working in kilometers per hour, we have to convert. And the time is going to be 5 seconds. So this is the time. Ignore the rotational motion of the wheels of the car. This is important, but we don't do rotational motion in South Africa, so it won't be a big issue. Now, 2.1, draw the free body diagram. Here. There we are. Draw the free body diagram. That is the first one. This is a previous grades topic. Calculate the magnitude of the net force required to accelerate the car. Calculate, this is also using Newton's law of motion. Calculate the magnitude of the acceleration of the car using Newton's law of motion. Calculate the magnitude of the change in momentum and draw a vector diagram to show the relationship between the initial, the final, and the change in momentum. So this is the question we're going to start answering. We already marked the data there. So let's start by drawing the free body diagram they ask us to do, and that will be question 2.1, which is a free body diagram. Now, the free body diagram, you always represent the object with a dot. Now, I personally like to draw the axis, but you don't have to. In actual fact, it's a little bit tricky because in South Africa, you can get penalized if you have extra arrows there. However, I'm going to do it. Here is the x-axis and here is the y-axis. This dot represents the object. Now, what forces are acting on that car? Now, on that car, we have the normal force, which is the force from the surface on the car, is perpendicular to the surface. We have the weight or gravitational force. I'm going to write weight here, which is straight towards the center of the earth. We have frictional force opposite the motion of the object because the surface is rough, and we have a force to the front that is a little bit tricky. It's not applied force, nobody's pulling the car, but the engine is making that car to move. So we're going to move here and just write force. Okay, now this is not the net force, this is just force. Right, so that is the free body diagram they want you to answer there. Now in question 2.2 say calculate the magnitude of the net force required to accelerate the car. Now to do that, question 2.2, we're going to write it here, 2.2. We're going to write quickly the data we have there. Now the mass, I'm not going to go back, you can go back. The mass was 520 kilograms. The initial velocity was 0 or is 0 because it was moving from rest. The final velocity is going to be equal to 100 kilometers per hour, and we cannot work in kilometers per hour. So how are we going to convert this one? You are going to multiply it. To convert, you are going to multiply by 1000 and divide by 3600. So to convert, you multiply by 1000 and you divide by 3600. This is how to convert. I'm going to write here from kilometers per hour to meters per second. This is important. It's also done in previous grade. Now, when you multiply that one, you will get that it's going to be equal to 27.78 meters per second. That is the conversion. We have the time, which is equal to 5 seconds, and they asking you to calculate the net force. That is the question here. They ask you to calculate the magnitude of the net force. So we are going to use once more Newton's law in terms of momentum. Okay, and this states that the net force is equal to the rate of change of momentum. Okay, you substitute this one is mass. We're working with the same object, so I'm going to skip a little bit of steps here. Final velocity minus initial velocity. These are vectors. I'm going to keep the symbols. Time, and then you can substitute. Everything is given to you there, and this is equal to the mass is 520. You can see there 520 multiplied by the final velocity, which is 27,78 minus initial, which is 0, divided by the time, which is 5, and the net force will be equal to 2,889,12 Newton. So it is in the same, it's positive answer, so it's in the same direction. The magnitude, I'm going to rewrite it here without the symbol notation, is going to be equal to 2,889,12 Newton. That is the answer. That is the answer there for the net force they're asking you. Okay, it's quite simple. It's quite simple. Question 2.3 say calculate the magnitude of the acceleration of the car using Newton's law of motion. Now, if the object is accelerating, then the Newton's law of motion you are going to use is Newton's second law of motion. Remember, you use Newton's second law of motion when the object is accelerating, and Newton's first law when the object is either at rest or moving with constant velocity. So 2.3, we're going to do it on this side here. Question 2.3, they're asking you to calculate the acceleration of the object applying Newton's law of motion. We're going to use Newton's second law. We say that the net force is equal to the product of mass and acceleration of the object. You're looking for acceleration, and the net force was calculated here in this question. So this is very, very simple. It's a 2,882,12 is equal to the mass of 520 multiplied by acceleration. So when you do that, the acceleration here will be equal to 5,56 meters per second square. And now they're asking you for magnitude, so we don't have to give a direction. That is question 2.3. Now question 2.4, calculate the magnitude of the change in momentum. We did use it here, but we didn't calculate it just like that. So we're going to calculate in question 2.4 the change in momentum, the magnitude. They don't want the direction. So 2.4, they're asking you to calculate the magnitude of the change in momentum. So we have the change in momentum is equal to mass, final velocity minus initial velocity, and this is equal to 520 bracket 27,78 minus 0, and this answer is going to be 14,445.6 kilograms meters per second, and that is the answer for this question. Is quite simple. And then 2.4, which is the final one, 2.5, they ask us to draw the diagram, the vector diagram, to see the relationship between initial momentum, final momentum, and change in momentum. And this is quite easy. This one is very simple. So this one is question 2.5. I think here will be enough space. Now what we have, that the car initially, the initial momentum of the car is 0, because the speed of the velocity of the car is 0. So the initial momentum of the car is just a dot. That is, initial momentum is not vector. There is not initial momentum of the car. And the final momentum, which I'm going to draw here, is going to be just an arrow pointing to the right or to the left, whatever drawing you said. I think in this question they don't specify the direction in which it's moving. So this here could be the final momentum of the car. So if you add the vectors, you only have one vector, which is the final momentum of the car I'm going to write right on the head here the initial momentum of minus initial because it's the same, and then when you draw the change in momentum starting from the tail of the first vector to the last one, in this case we actually have only one vector, and therefore that one here will be the change in momentum. In other words, the change in momentum here will be equal to the final momentum. From here, remember once more, change in momentum is equal to final momentum. Let's write the final momentum correct, plus minus initial momentum. You don't have to write it in this way. I just do it for you to see what is the issue there. Just wanted to show you that is the subtraction of the vector. So that is the diagram they ask you, the vector diagram for this relationship. So let's go to the last question we're going to answer now, and then we'll be sorted. So the final question said a cricket ball of mass 80 grams, the mass is 80 grams, as usual, let's mark the data, is thrown with a velocity of 24 meters per second. This here is the initial velocity. This is the initial velocity. After being hit, its velocity is 36 meters per second. This is the final velocity, is after. And we'll start using this a lot, before and after, but in the opposite direction. This is important, opposite direction. So we have towards and away, or forward and backward. It doesn't really matter, it's just a way to distinguish the direction, okay? Calculate the change in momentum of the cricket ball. Draw a vector diagram to show the relationship between the initial, the final, and the change in momentum. And if the contact time with the bat is 2 times 10 to the minus 3 seconds, what is the value of the force that acted on the ball? So let's start answering this question here. Now, question 3.1. We have the data. Let's just rewrite the data here, but organized. So we have, let's write the data. We have that the mass of the ball is equal to 80 grams. We don't work with grams, we have to convert it to kilograms. Remember, you have to divide by 8,000, so the answer is 0.08 kilograms. Now we have that the initial velocity is equal to 24 meters per second, and the final velocity is equal to 36 meters per second. Now remember, we have a forward and a backward, okay? So that is very, very important. So let's distinguish what direction we are going to work as positive and important. Remember, it's up to you, it's up to you. So let's write the forward as positive. Therefore, the initial is positive and the final is negative. This is a very important step, so please do it as you answer the question, or you start answering the question, do it first. And we're looking for the change in momentum. Looking for the change in momentum, that is question mark, and very fast as we did it before. Change in momentum is equal to mass, final velocity minus initial velocity. There we go. The change in momentum is equal to 0.08, open bracket, final is a negative, is minus 36, minus initial, which is positive 24, and then here we have the change in momentum is equal to minus 4.8 kilograms meters per second. This is the final answer. However, remember I said to be safe, let's write the given direction. So the change in momentum is equal to 4.8 kilograms meters per second, and I'm going to write away. However, you must remember to use the same term. They say opposite direction, so in actual fact you're supposed to write opposite direction, okay? So let's do that here. So opposite direction. Here's my cat now being naughty. I'm playing. Opposite direction. And so this is the final answer for this question. Opposite direction, remember, try to use the direction they're using. In the question they said opposite direction, they don't say forward and backward. So let's keep that one, okay? So now question 3.2. Question 3.2 is the one of the drawing, okay? So let's go here and draw the vectors quickly. What do we have? As usual, I'm always going to write change in momentum is equal to final momentum plus minus initial momentum. I'm always going to write that one first so I know. Okay, so now we're looking for the initial was towards the butt. I'm going to write towards this direction. Towards is very relative, so you don't really know which one is towards. So this is the initial momentum. Now the final, the minus initial, which is the one top there, the minus initial is going to be in the opposite direction. So this is minus initial momentum, and then you add in using tail to head. The final momentum is backward, is in this direction. Okay, it's bigger, it's much bigger. So that is the final momentum. Okay, and now using the method tail to head, here we have that you can have final momentum first. This is the final momentum. Right on the head, we're going to write the minus initial momentum, which I am going to just take it from here. I'm going to just take it from here and move it there, like that will be the addition vector. And then we are looking for the change in momentum, which is going to be from the tail of the first one to the head of the last one. This one is the change in momentum. Now if you can see here, you can also just move this one and the result will be the same, but I will leave that one for other tutors. If you move this one here, as you can have it there, head to head, so the head of the final with the head of the initial, that one will also give you the change in momentum here. You can see it is the same change in momentum. So it's another method, but I'm going to stick with the one I'm doing, or I'm been showing you up until now, but you are welcome to use the one your tutors, your teachers give you. Okay, I'm going to stick with the last one here at the bottom. I'm going to stick with this one, but the one top might be even easier because you just move head to head. You just have to remember that is the head of the final with the head of the initial. That's it. And then from the final, from the tail of the final to the tail of the initial, that will be the change in momentum. So guys, this one is the drawing. The last one is very, very simple. We're going to finish. This video is going a little bit long right now, and I don't like it. So question 3.3, they're just asking you to calculate the value of the net force using Newton's law in terms of momentum is equal to change in momentum divided by change in time. You read as rate of change in momentum. Change in momentum was calculated there. So all we have to do is to substitute. And as we said before, let's substitute the minus already. So it's going to be minus 4,8. That is what you got there, divided by the time, which is 2 times 10 to the minus 3. And the final answer will be minus 2,4 times 10 to the 3 Newton. That is the answer there. And as we said, let's keep the direction as we worked. So F net will be equal to 2,4 times 10 to the 3 in Newton in the opposite direction as we did with the first equation there. Opposite direction. But the answer could actually, in actual fact, could be leave as negative, because negative in physics means direction. Alright guys, this is the lesson. This is lesson 4. It's some revision. I think you need some revision before you carry on. Thank you for watching. Thumb up, subscribe for the channel. Next time we're going to be doing impulse before the law I already mentioned. We're going to be doing in parts. It's a relation between a change in momentum and a new physical quantity, and then I'll see you next time. Thank you for watching. Thumb up, subscribe. I'll see you next time.